Right, so I want to talk about regularity of a sort of classical differential equation. It's a classical degenerate differential equation. If I can get this one. So I want to talk about the regularity of a classical degenerate second-order differential equation. And so the focus to some extent is on the analysis, so on the regularity, how differentiable are solutions to this equation. But the moral of the story is that in order to understand the analysis, just if you're purely interested in the analysis, there's no way of understanding the analysis without understanding the geometry. So the geometry helps you understand the analysis of this differential equation. Okay? And so the differential equation is a level set equation. And so I want to start off with recording what that equation is and where it comes from. And so there's two ways of thinking about the equation. There's an analytical way, so that's the level set equation. And then there's a geometric way, and that's a mean curvature flow. So let me start off with recording this equation. So if you have a hypersurface in Euclidean space, if sigma is a hypersurface, my hypersurface will always be embedded. And here I'm just assuming that the hypersurface is smooth. And n here is the unit normal of this hypersurface. H is the mean curvature scalar, so it's the divergence of the unit normal, right? So I'm distinguishing here, although I probably won't really talk about the mean curvature vector, but I'm distinguishing between the scalar and the vector. The vector is basically this times the unit normal, or usually it's this times minus the unit normal. Okay. So this means that just to write it out, what this divergence is. So it's a sum here of the derivative of the unit normal in the direction of EI, inner product with EI, where EI is an orthonormal basis for the tangent space at this point where you want to evaluate this divergence. Okay. So now if the hypersurface, so remember that the hypersurface is embedded, it's smooth and embedded, so if you want, you could actually define a function, say just in a small tubular neighborhood, so that this function was 0, for instance, or whatever value what you want, exactly on the hypersurface. Right? So let's just say in general that the hypersurface is the level set of a function, and it's a level set corresponding to a regular value of that function. Well, if that's the case, then of course the unit normal is just the normalized gradient, so the gradient divided by the norm of the gradient. And the mean curvature scalar is just the divergence of this. Right? Now, if you have a one-parameter family of hypersurface, then one say that the one-parameter family is flowing by the mean curvature flow if the time derivative of the position vector is minus the mean curvature times the unit normal. So this here is also sometimes called the mean curvature vector. But anyways, but let's just keep it in terms of scalar. So this here is a one-parameter family of smooth hypersurfaces is said to flow by the mean curvature flow if the time derivative is equal to that. Here, it really should be the normal component to the hypersurface, but I'm omitting that, but it really should be the normal component here if you want to be very, absolutely correct. Okay, and so of course, right, and so this here, the normal here is of course the normal to the hypersurface at that time, right? And likewise, the mean curve to scalar is at that point in time, in space and in time. Okay, so that's what it means for a hypersurface to flow by the mean curve to flow. Mean curve to flow, the equation in this form, or in some form like this, the first reference I know of it is from the 19-teens in the work of Burkhoff, where he did a discrete version of this. And there's also work independently of that. There's work in the 1920s in material science where this equation comes up. Okay. And so now it has two key properties, this equation. One is that this equation, it's moving the hypersurface in the direction where the volume of the hypersurface is decreasing the fastest. So it's a negative gradient flow of the volume. The other key property is what's called the avoidance property. The avoidance property here is just a geometric formulation of the maximum principle. So this is a parabolic equation, so it's satisfying a maximum principle. And in geometric terms, the maximum principle is the avoidance principle. And the avoidance principle just say that if you have two hypersurfaces that are initially disjoint, then, and if you flow each of them, then under the flow, those two hypersurfaces remain disjoint. Okay? And so here's an example of this. So I'm imagining that I have a hypersurface, the red one, and I have another hypersurface, the blue one. They're disjoint initially. In this case, one is inside the other. It doesn't have to be, but so they're initially disjoint. And then the claim is that they will remain disjoint under the flow, right? And you can easily see this because imagine that they didn't. At some point, the outer one was catching up with the inner one, right? If the outer one was catching up with the inner one, then there would be a first point of contact, right? At some time, there would be a first time where the outer one would still be outer, but it would touch the inner one, right? But in this case, you see that the mean curvature of the inner one would be larger at that point than of the outer one, which means that right before this time, the inner one would move faster inwards than the outer one, contradicting that the outer one was catching up with the inner one, right? So this is the avoidance principle, and it's just a geometric formulation of the maximum principle. So in one dimension, this flow is called the curve shortening flow. And so there, of course, this iteration had been understood completely for a long time. If you're looking at, so if you are in, so my hypersurfaces are always in Euclidean space. And so in one dimension here, this means that I'm looking at a simple closed curve just because my hypersurface is always embedded. So it's simple in this case, the curve. And so as an example, if you take a round sphere in the plane and you flow it by the curve shortening flow, then under the flow it remains round. And if you're looking at the radius as a function of time, then it's satisfying a ODE. If you solve that ODE, you would see that in finite time, this round circle becomes extinct in a point. Okay? There's a more interesting example in one dimension, and this is the example of a figure that looks like a snake. So let me just get to that. I mean, I'm sure you know this already. We should get to something that you may not know. So if you have here, imagine that your simple closed curve is the boundary of the shaded region. Yeah, right? So it has sort of snake-like figure. And this here is like 6 time shots of the evolution where you're moving, right? You're moving from here to here, and so on, right? So under the curve shortening flow, it will start unwinding, and in finite time it will have unwinded completely, and then it will disappear in a point, right? This here is sort of may initially seem surprising that it managed, before it disappeared, it managed to unwind. But the explanation for that is that, so that if you're looking at a point here at the end, then you will see that the geodesic curvature at this point here is much larger than the geodesic curvature at a point here, which means that this here is moving much faster than points here are moving in, right? And this makes it seem plausible that it can unwind before it disappears. Right? I should also have said that just from the avoidance principle, if you take a simple closed curve in the plane, you can enclose that by a round circle. And now the avoidance principles say that those two curves, if you're flowing both of them, then they will stay disjoint. But the round circle will disappear in finite time. So this means that the one that is enclosed by the round circle will also have disappeared in finite time. Right? So any simple closed curve in the plane in finite time will disappear. Okay, now there's a remarkable theorem of Grayson from the early 80s that say that this evolution that we just looked at, in this case of this snake-like figure, is a completely general principle. Namely that if you take any simple closed curve in the plane and you flow it by the curve shortening flow, then in finite time it becomes extinct. We already know that. But right before it becomes extinct, it will look like an almost perfectly round circle, and then it will shrink to a point. Right? And the theorem of Grayson also say that under the flow, this simple closed curve will stay smooth. Right? So it will stay smooth up till the final time when it becomes extinct in a point, and right before it becomes extinct, it will look almost perfectly round. Okay? Now, so now let's go to the case of higher dimension. So suppose you take, again, a hypersurface, and now choose a function. So choose a function. So this is sort of the beginning of something that has been extremely widely used in applied math. So if you take a hypersurface here, embedded hypersurface, define a function, say, so that it's positive in the inside, in the region that is bounded by this compact hypersurface, and is negative outside, and it vanishes on this hypersurface. Right? So take such a function. Now imagine that you are flowing simultaneously distinct level sets of this function. Right? Well, by the avoidance principle, different level sets will stay disjoint under the flow. Right? That's what the avoidance principle tells you. And so now, if we look at a function u, so that each of the level sets, so if we're looking at a function u that is defined on our Euclidean space cross time into R, and so that for each S over here, if you're looking at the level set, this level set of this function here, and you're looking at the level set here, so this is what I wrote down, so the x here, where this here is equal to s, so for each fixed s, you're looking at this you're thinking about as a hypersurface, right? For each s, this here is a one parameter family of hypersurface, because for each t, you're getting a hypersurface here. Right? So if they are flowing by the mean curve of flow, then we say that the function u satisfying the level set equation. Okay, so this is a very standard thing to do in applied math, and if you just plug this in, then you will see that the function you have to satisfy this equation. Right? This is assuming, of course, that you are not at a critical point. Right? And so now you see that this here is a parabolic equation. It's degenerate because you're dividing here with the gradient, with the norm of the gradient, right? So when the norm of the gradient actually vanishes, this is a degenerate equation, right? And so this equation, again, it has been very widely studied in applied math. There's a sort of very well-known paper of Boscia and Setien from the 80s where they studied this equation numerically. When I looked last at this is cited, this paper actually cited more than 12,000 times. It's a very widely used paper in particular in applied math. Okay? But this equation actually, the first reference I know to this equation comes earlier and exists in the material science literature. Okay? But Boscia and Setien was the one that sort of systematically, that first systematically studied it numerically. From an analytical point of view, this equation was first studied by Evans and Spook and Chain, Giger, and Gödel, and they constructed viscosity solutions. They constructed generalized solutions to this equation and proved uniqueness. Right? And so you may recall that there's two ways of defining a viscosity solution. One that go back to Calabi in the 50s, and is where you're basically looking at there have to exist a function below your given function. If there exists a function below your given function, there exists a function below your given function and touches it in one point, and is satisfying some differential inequality, then you say that the function that lie above this function satisfying this differential inequality in a weak sense. There's another slightly different notion of viscosity solution that is due to Mike Prandtl and Pierre-Louis Limons, and also Evans. I think Evans was probably the first that defined. They were unaware of Calabi's work. Usually, Prandtl and Pierre-Louis Limons, I think, get the credit for this second notion. Their achievement, as opposed to Evans, was proving uniqueness. I think Evans couldn't prove uniqueness, and the other guys proved uniqueness. Okay. Anyway, so for this particular degenerate equation, solutions, generalized solutions was constructed by work of Evans and Spook, and independently at the same time of Chain, Giger, and Gödel, and they used this viscosity solutions, and it was sort of one of the big breakthrough for viscosity solution, that they could be used to define solutions to this equation. Okay. Now, let me just look. So we looked at two simple examples of how things evolve under the flow in one dimension. Let's look in higher dimension what happened. So there again, if you take in Euclidean space, if you take a round sphere and you try to evolve it under the mean curve of flow, then again, just like in the plane, under the flow it will remain round. And if you again look at the ODE that the radius satisfying, you will see that in finite time, a round circle, a round sphere will become extinct. And so this of course means that by the avoidance principle, if you take any enclosed hypersurface in Euclidean space, you enclose it by a round sphere, you know that the round sphere in finite time become extinct, then the closed hypersurface that was enclosed by this round sphere will also become extinct in finite time. So this means that some kind of singularity must have happened. Right? Okay, now likewise, if you're looking at a round cylinder, then under the mean curve of flow it will remain round, and in finite time it will become extinct, and this time it will become extinct in a line. Another example is that of a thin torus of revolution. This is what is usually referred to as a merit string. So there's a picture of the merit string. So it's a torus of revolution. You are evolving a curve. You have here, you're evolving a curve like this, that you're evolving around an axis like this to get the shape here. And so if you're looking at the evolution of this, then you'll see, just by the symmetry, that it will remain a surface of revolution under the flow, and in finite time it will become extinct in a round circle like this. Okay. And right. So, and let me look at a fourth example. So I have the sphere, I have the cylinder, I have the merit string. So this is the fourth example, and that's the example of the dumbbell. So let me just look at first a picture of the dumbbells, and here we have a dumbbell. I'm looking at here a dumbbell which is a surface of revolution. It's a surface of revolution along an axis like this. So if you evolve it around this axis, some curve, then you get this dumbbell. Surfaces, by the way, like this, that are surface of revolution around an axis like this, the mean curve of flow equation reduces to a one-dimensional heat equation. Okay, and so those surfaces can be completely understood, and has been completely understood for about 25 years through work of Angelin, Altshuler, and Giga. So just using one-dimensional techniques and parabolic Storm real theorem due to Angelin that only hold in dimension one can completely understand the evolution of such surfaces. And so what happened here, and this is a very general thing that happened for all these kind of surfaces, something similar might happen for any other surface that is obtained as an evolution like that. So what happened is that when you evolve it, after some time, the neck here will pinch up. It will separate into two components that will become immediately smooth, although with very high curvature here at the tip.
Is there enough quasi-locality that you can actually say that there's an unambiguous continuation of the singular time?
We will get to all of this. But that's right. So here, so you may ask, you may say, okay, wait a minute, when you define the mean curve flow equation, you looked at smooth surfaces. Of course, what Angelin, Altshuler, and Giga uses here, they use this notion of solution to the mean curve flow equation that was exactly coming from the level set equation, right? So the level set equation, this gives you a way of flowing past singularity, because you're looking at a function that's satisfying this degenerate parabolic equation, and you're looking at the level set. The level sets are, by definition, the evolution after some time, right, of this hypersurface. Okay, and so this is what they use, and this is, and they get this then this picture here is made rigorous using that, and it's made rigorous for all surfaces in R3 that are rotational symmetric around an axis like that. Right. So yeah, right. So Claude is of course right here. I should emphasize that point, that the level set allows you to give meaning to what it is when you're flowing past singularity and where you don't actually have a classical solution. Okay. So now, okay, so let me just sum up. Let me just sum up what it's saying. So it's saying that so the conclusion of this picture is that under the mean curvature flow, if you're flowing the dumbbell, then after a finite time, the neck will first pinch off, the surface will disconnect into two components, and later each of these two components will actually disappear. Right before they disappear, they will look almost perfectly round. Okay? So this is, and another thing which seems very plausible for this picture, if you're looking right before the first singularity happened, where it's breaking into two components, if you imagine that you're standing at the point in space where it's breaking into two components, and then you just move slightly before it's breaking into a component. And if you now imagine you're enlarging this picture, then you would see then the bell would sort of shoot off. If you enlarge the picture, the bell would move off to infinity. And what you'll see is that this part of the surface will look like an almost perfectly round cylinder. So all of this, in this particular case, was known and is in this paper of Engel and Giger. So this is in this rotational symmetric case where everything is reducing to a one-dimensional parabolic equation that can be understood by very classical methods. So, right. So now, in general, of course, if you take, as we said, from the avoidance principle, if you take a closed hypersurface, under the flow it's contracting, the area is going down, it's contracting, it will develop singularity, and it will eventually become extinct. Right? That's what happened in general. And the singular set is the set where the flow is not smooth. So this is the set in space-time when the flow is not smooth. Right? Now, so now in these in the first three examples, the example of the sphere, the cylinder, and the Lewis ring.
Wedding ring.
Yeah, it's actually, for some reason in the literature, it's always referred to as an marriage ring. So so it's not my chosen word. It's your argument. It is
not invented by native
some
speaker.
other people. Right. So in those examples, in the case of the sphere, the singular set is a point. In the case of the cylinder, the singular set is in the line where the round cylinder becomes extinct. And in this third example, the singular set is in this simple closed curve where the ring is, maybe I won't refer to whether it's a wedding or marriage ring. The ring, let's agree on it's a ring. Okay. But you see also that in these examples, the singularities occur at just one single time. Right? And so now you see in the contrast, in the example of the dumbbell, you had one singularity where the bell was disconnecting into two components, and then you have two later singularity, or one later singularity, where each of the bell became extinct. Right? Now, so in my example here, I had an additional, at least in the picture, it looks like there's an additional symmetry. There's also a symmetry, which is a rotational symmetry here, There's also symmetry, which is reflection symmetry around this axis. So it means that these bells are exactly the same. So this means that they will become extinct at the same time. Of course, you would also look at something that was rotational symmetric here. This bell, say, was much larger than that. In this case, you would get 3 singular times. Right? It will disconnect into 2 components. This component would be much larger than that, and therefore it would become extinct later than this one. Okay? So, but in any case, you see that in the case of the dumbbell, you have more than 1 singular time. Right? Okay, so now let me define what it means for a hypersurface to be mean convex. So we say that a hypersurface, while it is convex, if all the principal curvatures are positive, it's mean convex if the sum of all the principal curvatures is positive. Here, it doesn't really matter whether it's mean convex or weakly mean convex. I mean, it is also fine if you just want to look at whether the mean curvatures are negative as opposed to strictly positive. And so now you see that if you take a hypersurface, that is, if the initial hypersurface is mean convex, then actually the flow will have this property that it will move inwards, right? It will initially move inwards. And it's easy to see, actually just follow from the maximum harmonic maximum principle, that mean convexity under the flow is preserved. So if its initial hypersurface is mean convex, it will move inwards. The later hypersurface will also be mean convex, so it will keep moving inwards. Okay? Right, and so now, and so this means that it will actually sweep out the entire domain bounded by the initial hypersurface. Okay? So now, and I'm going to focus, if I have time, I can say something about the general case later. But let me focus the rest of the discussion, unless I have extra time, in the case where the initial hypersurface is mean convex. Okay? So then, because it's moving inwards and because it's sweeping out the entire domain bounded by the initial hypersurface, this allows you, and this is, all of this is very, very classical. It's in the paper, you can find it in this series of 4 papers of Evanson's book from the early 90s. It's also, by the way, it appears many places in the applied literature. Sentin have a number of papers about this. So it's kind of very standard, this sort of thing, that if the initial hypersurface is mean convex, it's always moving inwards, and this allows you to rewrite the equation. Instead of as a parabolic equation, you can rewrite it as a degenerate elliptic equation. And so the way you do that is that you define a function u of x. So u of x, so you have this here is the initial hypersurface. You know it's moving inwards, it's sweeping out this domain bounded by this initial hypersurface. You're looking at a point here in the domain bounded by the initial hypersurface. And now the function here in this point is the time when the evolving hypersurface arrives at this point. Okay? So this is called, it's in the literature, it's called always called the arrival time.
When you say mean convex, you just mean that the mean curvature has a sign.
Yeah, that's right. Okay, right, so this is called the arrival time. And now you can see easily that if you look at the function b of x comma t equal to this function minus t, this satisfying the level set equation. Okay? So again, this is very classical. It's, it was known 25 years ago already. And so if you write down what this means in terms of the function u, right? So b satisfying the level set equation, you have uniqueness, by the way, right? of this of solution to the level set equation. So this means that U actually will satisfy this degenerate elliptic equation. Okay? And again, of course, it's degenerate. It's degenerate because it's not really defined where the gradient of U vanishes. Right? And particular solution is, so I should also say that if you have a solution to this equation, then of course U plus a constant is also a solution to this equation. Right? U plus a constant just means that you have kind of shifted by some constant the time when it's arriving at a point, right? And sometimes if you want to focus at a point, it's kind of natural to normalize so that it arrives at time 0 at that point. So then of course the initial hypersurface is not at time 0, but it would be at some negative time.
So the flow is smooth except at one point in the interior? Is that
No. This, here I'm just looking at, what I want to do is, I want to understand what is the regularity of this function. I'm not assuming any smoothness. I'm not assuming any smoothness. I'm assuming that the initial hypersurface is smooth, but I'm not assuming that the flow is smooth. At any time, it may be singular all over the place. We'll get to this in just a second, because I want to, there's an obvious way of reformulating this. Okay, so I get that this, so this is going to be the main focus of the rest of the talk. It's going to be this degenerate elliptic equation. And I'm interested in understanding what is the regularity of this equation. We know already that we have existence of uniqueness of solutions, but they are only defined in this very general sense. And what Evans and Sprook and Chengiga and Goddard was able to prove was that the solutions to this equation are Lipschitz. But it turned out that they're much more than Lipschitz, okay? So now let me look at a particular solution, just to give you an example. And it's actually an important example. So this is in R3, say, and if I'm looking at this function here, this quadratic function, this here is, it actually geometrically, this is the arrival time of the round cylinders. If you're looking at the evolution of the round cylinders, you normalize it so that they arrive at time 0 at the axis where they become extinct. Then this is the arrival time function. It just corresponds to that the level set of this function are actually round cylinders. Okay? So this is a nice solution to this equation. Right? Okay, just to give you an example. And so again, Evans and Sprook and Chengiga and Goddard, they were actually able to prove that these generalized solutions are Lipschitz. Okay? Now again, there's two ways of thinking about this whole problem. You can either think about it analytically. If you think about it analytically, you think about these degenerate either elliptic or parabolic equations, and you think about functions that solve those equations, and you think about what is the regularity of those functions. Or you can think about it geometrically. If you think about it geometrically, then you think about it as a flow. Okay? My focus here is actually to think about it analytically. Okay? But in order to understand the analysis, we need to understand the geometry. So we need to understand the flow. Okay? Now, a point here is, remember that, so a point here is singular. Remember that u of x is just the time when the flow arrived at x. So this is a point in space-time. Right? So this point here in space-time is singular for the flow precisely if the gradient of u vanishes. It's not terribly surprising, right? Because you're dealing with a degenerate equation. It's degenerate exactly when the gradient vanishes. So, but nevertheless, it's, this is the geometric way of thinking about it, right? That it's a singular point for the flow. This is the analytical way of thinking about it, that it's actually a degenerate point for the equation. Okay. So Right, so just to check that this is sensible, if we're looking at that particular example that we looked at before, where u was the arrival time function for the round training cylinders, in our tree, this meant that u was equal to this. Then you see that the singular set for the flow, well, the singular set for the flow is this line where x1 and x2 is 0. And that, you see, is exactly where gradient of u vanishes. Right? So at least in this example, this sort of statement check out. Okay, so here's one of the main theorems I want to discuss. Sort of the main theorem, and then but then there's some stuff that go into the proof. So remember again that Evans and Spook and Chang and Goto, they constructed solutions to this degenerate elliptic equation, and they were able to prove that solutions were Lipschitz. Right? So this theorem here is that you can actually do a lot better. So it turned out that solutions are not just Lipschitz, but they're always twice differentiable. They're always twice differentiable. The second statement here is, by the way, classical. So the main the point of this here is that they are always twice differentiable everywhere. It's a classical fact that they are smoothed away from the critical set. This just because away from the critical set, the equation is not degenerate. Okay, so then it's by classical techniques. So the main point here is that actually the function that was only known to be Lipschitz is actually not just differentiable, but it's actually twice differentiable. And remember that one of the sort of big achievement was that they were able to prove these Evans and Spook and Chang and Goto, they were able to make sense of this solutions to this equation using the viscosity methods. But it turned out that actually you don't need the viscosity method, because not only are the functions twice differentiable, but they actually satisfy this degenerate equation in a classical sense. It is a degenerate equation, right? I mean, you cannot do anything about it, but they actually are a solution in a classical sense. Moreover, actually, it turned out that at the critical sets, at the critical points where the equation is degenerate, the Hessian is in a particular nice form. It only has two, it's actually symmetric, which is not absolutely clear because I'm only claiming here that it's twice differentiable. It's symmetric, and it only has two eigenvalues, 0 and -1 over k, and this -1 over k comes with multiplicity k plus 1. And this k here corresponds to the dimension of a spherical factor. Okay. Now, let me just tell you a little bit more about what was known. So Evans and Spook and Chang and Goto, they proved that solution was Lipschitz. Some 25 years ago, Christian, so this was more or less at the time of Evans and Spook and Chang and Goto, Christian proved that if the initial hypersurface is convex, then the arrival time function is actually C2. And so Christian, to prove this, Christian used that if the initial hypersurface is convex, then by this earlier result of Christian, if the initial surface is convex, then under the flow it will remain convex and it will become extinct in a round sphere. Using that, Christian actually were able to conclude that if the initial hypersurface is convex, the function is not just twice differentiable, but it's actually C2. Tom Millman, a couple of years later, this was part of Tom's thesis. So he gave an example of a particular dumbbell that had that was not just rotational symmetry around an axis, but has some further symmetries. So using that, he was able to prove that there exists a hypersurface in our tree that is mean convex. I should also have said, and I forgot that, I should have said that the dumbbell, you can, I mean, a lot of dumbbells are actually, depending on exactly how you construct the dumbbell, but the example that I gave of a dumbbell, it was actually mean convex, okay? And the example I gave of this marriage of Reading ring was also mean convex. It's just for the ring, it's just a matter of that the profile circle is sufficiently small, okay? But anyway, so what Tom proved in his thesis was that there is a surface in our tree that is mean convex. It's actually rotational symmetric. It has some further symmetry, so where the function, the arrival time function, is not C2. Right? So this sort of proved that you cannot do better than twice differential. But I should also say that actually I didn't state this, but you can also prove that it's twice differentiable. It's twice differentiable with a uniform bound on the Hessian. Okay? But in general, right, it's not actually C2 by this result of Tom from his thesis. In the plane, if you're looking at simple closed curve in the plane, then Sylvia Stephati and Bob Cohn, they proved that the function U is actually C3. So this is in the case, say, where the initial curve is convex. And Natasha proved that if the initial surface is convex, there's examples where the initial surface is convex, where U is not actually C3.
I'm a little bit...
but it's actually not three times, I mean C3 or even 3 times differential.
So I thought you were going to say that the solution had to be C2, but the example of Illman...
It's not.
So
it's twice differentiable, but the second derivative may not be continuous. I'll get to this in a second.
Oh, I see. It's twice differentiable, but not C.
Yeah, right. And it's a sort of subtle thing. We'll come to this in a second. It's twice differentiable everywhere where you know, at critical points, the Hessian is incredibly nice, right? It has this form. There's only finite many possibility for the Hessian in particular, right? At the, you know, after, you know, we're taking, I mean, at least, yeah, right? And, but anyway, we'll get to this in a second. So I just want to say that, so what Natasha, so one way of sort of reformulating what Natasha proved was that Friskin's result is optimal. So if the initial surface is convex, then U may not be actually, I mean, I say here C3, but actually she even proved that it's not 3 times differential. It's not a matter of whether the third derivative is continuous, it's a matter of whether the third derivative exists. Okay? And so she gave examples where the third derivative did not exist. Now, so you can sort of complement this result of Tom. And so you can complement it. So it turned out that actually the situation become very rigid. So remember that the function is always twice differentiable. Right? But it actually turned out the situation become very rigid. Because if this function is not just, is actually also, if the second derivative is continuous, so if it is continuous, then the flow is singular at exactly one time. It's only one time. The singular set, this here I should have said, I'll come back to the general case. The general case is exactly the same, but just for simplicity, I state this here is this statement here is true in general. Let me just specialize in R3, and then I'll come back to the general case is similar. Okay, but let me just say in R3 first. So if the arrival time function is if the second derivative is actually continuous, we know the second derivative is always exists, always is bounded. But if the second derivative is actually continuous, then there's exactly one singular time. this singular set at this singular time is either a single point with a spherical singularity, or it's a single closed curve of cylindrical singularities. And so you compare this with the case of these three examples that we looked at. Right? So if you see that in the case of the sphere, and this is, by the way, if and only if statement. Right? The second derivative is continuous if and only if this happens. Right? And so you see that in the case of the sphere, this actually exactly falls in, this really falls in under this situation here. Right? It becomes extinct at just it becomes singular at just the final time, and at that point, it corresponds to a spherical singularity. In the case of, of the ring here, you see that it also is singular at exactly one time, and it falls in onto this category. And you see also in the case of the dumbbell, so this is any dumbbell, and in fact it holds for any of the rotational symmetric things that Angeling, Altshuler, and Giger studied, that you, in that case, for any of these rotational things, unless it's basically like, I didn't make this more precise, but basically, more or less, it is, except in the case of the sphere, you will always get several singular times. And so it doesn't actually satisfy this. Right? So, okay.
Sorry, 1 and 2 are for surfaces only.
Yeah, and now I come to the general case. I just want to, so I come to the general case. General case is similar, the proof is the same. Okay, I just stated it here just because my examples was not three. Maybe I thought it would be easier or not here, whatever. But I also want to, before that, I want to just reformulate it analytically. Right? So what does this mean? So when I'm talking about that it has exactly one singular time, then I'm thinking about it geometrically, I'm thinking about the flow. Right? So analytically.
So when you say that the singular set can be, the typical thing is it's a curve. What class of curve?
Right, I'm not actually saying that, it's C1. It's C1. This is, right, I mean, this is a hard fact. And this is so I'm stating these two theorems. Right, so these are two theorems. If you're interested, you can find it. So this one here was from last year, and this here is from a paper this year. But
only one connected component? Is it always just one connected component and always?
No, well, in this case it is, right? I mean, when I say it's a simple closed.
Oh, simple closed.
Simple closed C1 curve. In this case, it's just one curve. Right? But actually,
I had it written, I just didn't process it.
It's in this case, it's exactly one curve. But it is in the proof of this, and maybe I can get to it. I certainly won't get to. It uses several other results that are not part of these papers, that are not easy to prove, and are things we proved earlier. One is from a paper that appears in Annals from last year, and then another paper that actually appeared in this year in insurance. But they're not part of the statement here. Maybe I get it. They're ingredients in food. Okay, and I hope to get into that. But let me just restate it, because, my interest here is in understanding the analysis. And again, I still owe you to explain what role the geometry plays. Right? And I owe you to explain that the geometry, actually understanding the geometry is key to understanding the analysis. Okay, so now let me reformulate this last thing analytically. So this function here, the second derivative, we know the second derivative always exists, is always bounded. The second derivative is continuous if and only if there's exactly one critical value corresponding to a maximum for this function. So there's exactly one critical value. And either the critical set is a single point, and the Hessian is in this case very nice, right? It's just minus a half times the identity. We're still here now 3. is a simple closed curve. And along this simple closed curve, the Hessian is also very nice. It only has two eigenvalues, 0 and -1, and they come with multiplicity of 1 and 2. And the kernel here is corresponding to the tangent to the curve. Okay? So this is it's just an obvious reformulation of the theorem, sort of purely analytical without thinking about the flow. Okay, now let me say, so what is the version in high dimension? The version is exactly the same. And so it is that the second derivative is continuous if and only if there is only, now I'll go back to thinking about it as a flow, and I won't state the equivalent version in terms of the critical set of the function. So U is C2 if and only if there's exactly one singular time, and the singular set is an embedded closed C1 k-dimensional submanifold with pseudonymous singularities. Okay? So this is the general case. Now, let me just look, so I won't, so I only have 4 minutes left. And I want to emphasize one key thing that is not part of this theorem, but plays a key role in the proof. Okay. So how do you prove that this function is twice differentiable? Okay, everywhere. So now it has been known actually for some time that if you're looking at a function like this, so if you're looking at this arrival time function, and you're looking at the level sets, so in the case where, we can come back to the general case later, but in the case where the initial hypersurface is mean convex, it has been known for quite some time that if you looking at the, remember that the critical point for the function is a singular point for the flow. So let me just think about it analytically. So if I have a critical point for this function, this is where I need to prove that it's twice differentiable. Away from the critical set, it's standard. Okay? So now, suppose I have a critical point for the function. It has been known for quite some time that if I'm looking at the level sets of the function right before that critical value, so values slightly below that critical value, then near this point, it is known that they almost look like round cylinders. Right? Round cylinders, this even include the possibility where it's a round sphere, right? But I'm just now, what was not known is that, but you see, when you have to prove that a function is twice differentiable, right? Then you're trying to prove that a function is up to higher order at that point is equal to a particular quadratic function, right? So it doesn't do you any good just to say that the level sets are almost cylinders, right? I mean, it says something, but it doesn't really have anything to do with twice differentiable, right? But if you just think about it, so if you're trying to prove that a function is differentiable, what are you trying to prove? You're trying to prove that on all small scales, a function looks like the same linear function, right? And so in this case, you're trying to prove that, that the function on all small scales look like the same quadratic function, right? And so this is, so now this here is, so what is the key to proving this? So this is the theorem that we proved earlier. So let me just illustrate this. So this here, so this is a uniqueness of these cylinders. So this is sort of a major question. And the question here was that you know that the level sets are, or if you will, that, so analytically you know that the level sets almost look near this critical point. They almost look like cylinders. But you don't know that whether the cylinders changes from scale to scale, right? So this is, so of course if you want to think it geometrically, you just think about it for the flow. And so for the flow, the thing is here that you have a singular point for the flow, And now you're asking, as you are going towards a singular point, then you know that the evolving hypersurface, if you, after you rescale it to unit size, then near this point, it almost looks like a cylinder. But as you're going closer to this singular, as the time go closer to the singular time, it could potentially, the cylinder could potentially have rotated. Okay. And so this falls into a class of sort of general uniqueness questions where this is really the first general case that has been proven. So this important work on this, I mean, there's a lot of work, but there's two that are particularly important. This is a work of Algren and Algren from the early 80s, and also of Leon Simon from the early 80s. Algren and Algren, they had an integrability condition, and then, so it was terrific work, but it's relatively, once you have integrability, it's relatively, I mean, at least in hindsight, it's relatively straightforward to prove uniqueness. And what Leon proved was, so his support of the Algren and Leon was the case of minimal surfaces where you get uniqueness under various assumptions.
Excuse me, but in this case, the singulars would intersect.
These are not drawn into the same scale.
But this is after and this is only, remember that this is just near, right? So imagine that you have, imagine you have a Doppler, right? Now, of course, this doesn't seem plausible in the case, and that was now a long time ago, in the case where you have this sort of rotational symmetry. But you see that this here is a singular point for the flow, right? If you magnify the picture, then it looks like you're getting this sort of cylinder, right? I mean, of course, it's not the cylinder all the way out to infinity. This is a key difficulty in this, right? But you know, if you magnify it up to kind of unit size, then it looks like this cylinder. Now, of course, it could potentially, if you now go to a slightly later time and you magnify it, it could look like this cylinder here, right? But you see, so it's not, you know, so this is, here I'm magnifying up to unit size, and then I'm even sort of letting things go off to infinity, right? But this doesn't really, I can't let it go off to infinity at this point, right? They're not actually, they're never cylinders, right? They're topological spheres, right? So it only looks like this on some scale, okay? Okay, so let me just say, so what Bill and I, so this is all, and I sort of apologize, I should have mentioned it. This is all, everything here is joint work with Bill and Gotcha. And so what Bill and I proved was that these cylinders are always the same, independent on scale. I mean, that they approach some unique limit. And so the crucial point for us is, so this is not, this is a non-integrable case. It's not integrable, you know, it doesn't fall in under the Algren. What Leon did is, Leon proved, Leon's work is also wonderful work, and Leon reduced the question for minimal surface to a theorem of Wojciech. But the Wojciech is something, Wojciech theorem that is in algebraic geometry and is dated back to the 50s. It's about analytical functions on a finite dimensional Euclidean space. Leon was able to reduce his question to a finite dimensional case and then apply the result of Wojciech. Bill and I was not so lucky, so you cannot, in this case, you cannot reduce it to the Wojciech argument. So instead, what we had to prove is we had to prove a Wojciech type inequality. It doesn't actually, it only looks, if you reformulate the problem, you can actually see that it falls in onto a kind of Wojciech kind of inequality. But the proof had absolutely nothing to do with the Wojciech say infinite dimensional version. It's a true infinite dimensional version. It's not, there's no reduction here to either the Bolshevik arguments or anything else in real algebraic geometry. Okay, anyway, so I think I'm really out of time. There was various other things that go into it. But I hope that this here, that is somewhat convincing that this uniqueness here should play a key role in differentiability, just like that for a function of one variable to prove that a function is differentiable is something about proving that it looks on all small scales like the same linear function. So again, the moral here is that if you are just interested in the analysis of this equation, then there's no way you could understand this analysis without understanding the geometry. Right? And so without it, they're only able to prove Lipschitz.
Any questions for the speaker?
So the Hessian is not continuous, but presumably it's bounded.
It's always bounded. Yeah.
Can you say anything better than that?
You can say something. You can say something better, and you can say something. I mean, so actually, in the general case, you can actually describe the critical set or the singular set for the function. You can actually describe this quite well. And you get some, you get extra regularity. You get a lot better regularity. It's actually always C2, by the way, if you're approaching the singular set orthogonal. I mean, with a non-trivial angle. Okay. If you're going in tangent, that's a problem. That's where it's not C2. Okay. But there's all kind of Anyway, I mean, there's also various things from a purely analytical point. There's also other things you can ask that are of interest, and it is related to this. And so this is for this sort of degenerate equation. You can ask. Well, it's not actually. So initially we were hoping to prove a lot more regularity. Of course, it turned out to be not true. But we had some particular applications in mind. But you can still ask. Even though it's not even C2, or if it is C2, you can ask does it share? If it is C2, you can ask does it share properties that analytical functions have? And it turned out it seems like it does. I mean, it seems like that there's a lot of things that you can prove that is known or conjecturally known for analytical function that this function actually satisfies. And that then has some geometry applications.
Other questions? Do you have a bifurcation example, like one parameter family of hypersurfaces, where for negative values you have only one singular time, and for positive values you have more than one singular time? So if I understand you correctly, I mean, of course you can look at these rotational symmetry. Yeah, but that's more than one singular time.
Yeah, but of course if you connect it, I mean, if a round sphere has only one singular time. So you can connect these through rotational symmetric hypersurface. Right?
You mean convex then?
I mean, that's interesting thing. It's not an uninteresting point, and there's some somewhat weird phenomena that happen. So this is an example of Hamilton that proves that you can have a case where there's just one singular time. There's just one singular time for the flow, but at that singular time, if you rescale to unit size, you wouldn't actually. There's only one singular point in space-time, but at that singular point in space-time, you would see a non-compact silhouette. So this was kind of done by this sort of argument interpolation between two different cases. Anyway, so it's a kind of, yeah, you can get some interesting stuff from this kind of interpolation.
The next talk is 11:30. Let's thank the speaker again.